are now going to see the frequency and the Doppler effect at which the listener is going to listen the sound waves when the listener is at rest and the source is moving. So here we have the source of the sound waves, and here we have a listener. Here we have a listener. So now, if we have that the source is moving, so here we have this wavelength. This is a wavelength here. The wavelength here is fixed, but if now we move the source, so we have these waves, sound waves. Let's say that I'm moving towards the listener. So I have these sound waves are coming here, are coming together, each time closer, and here they are coming far away because the source is moving towards here. So we have two different wavelengths. For this person, how he's going to listen is we have the person is stationary, so we will just count the velocity of the wave propagation and the velocity of the source. So at a time t is for the period in the sense, because let me talk about a time at which there is a from crest to another crest. So here in this time interval, the sound wave move a distance of v times t. This is the distance. Velocity times time is distance. And the source move a distance or advance a distance of velocity of the source times t. Now t, remember that t is the period, so is 1 over the frequency at which the sound waves are produced by the source. So this is v over f. This is v sub s over f. So we want to know the frequency at which this person is listening. So we have the wavelength here is getting shorter. So we have wavelength, the listener is, or the wavelength that the listener is going to perceive. We will talk later about the frequency, but just this wavelength is the, let me call it wavelength perceived. Would be the wavelength actually of the sound wave minus a delta wavelength, that this delta wavelength is the distance of that have moved the source. That is, here for example we have, this is the wavelength, but if the source is coming close, so if the source is coming close, now I would have, instead of the wavelength, the wave that is being here, it would be here. So the wavelength now is what it was before, this minus that. So there will be now the new wavelength from here to here. So I have this. So I have that lambda is lambda minus this, that is v sub s divided by f. Now the listener, and this is this the v sub f. So the listener will listen to a frequency. Remember, we have the frequency is velocity divided by lambda. In this case, we are looking for the frequency of the listener would be equal to the velocity, that is the velocity of the sound wave, that is the propagation. So v, it would be v divided by the wavelength, and wavelength is this. So we have v sub f, sorry, v divided by f minus v sub s divided by f. So it will be v times f divided by b minus b sub s, or f sub listener is 1. I divide everything by b, so I have 1 over 1 minus the velocity of the source divided by the velocity of propagation of the wave times the frequency at which the source is emitting the sound waves. So in this case, the frequency is going to be higher because this 1 minus whatever it be is a number less than 1. If we divide 1 by something that is less than 1, it would be a greater number, and so we have a higher frequency, and so this listener would hear a higher pitch. On the other side here, we have, if a listener is here and this source of the sound wave are moving away, and then we have that the wavelength is lambda plus the delta lambda, that is the distance that the source wave have advanced. So it would be here plus, 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 plus. So the sign depends on if the source is moving towards the listener or away from the listener. So now this is the formula, minus or plus, for a frequency heard by a listener when the listener is stationary and the source is moving.